Hello everyone, it's my great pleasure to welcome all of you here and also Alen. Alen Alempijevic is a livestock professor here from Australia. He's a professor at the Robotics Institute at the University of Technology in Sydney and is again visiting us here for a couple of months. He holds a PhD, which he also got granted from the University of Technology in Sydney. In the past, he has been working also on autonomous vehicles, not only on livestock, but one of the first person participating in the Delta Urban Grand Challenge together with people from Berkeley. And he also has been a research fellow at the Center of Excellence for Autonomous Systems. In general, he is a person looking into robot perception with a strong background in multimodal data fusion and also use of AI techniques in order to enrich the information that we get from the sensors looking into spatial temporal fusion. He has worked on localization and tracking algorithm, things like modeling deformable objects and reconstructing deformable objects. And so a couple of years, he is looking into agriculture as well. A little bit less into crop production yet, but that's what we hope to change. But is looking into livestock and livestock estimation, and especially looking into approaches how to capture individual data from every individual animal related to the production processes. And that's what he will probably talk about today. So I'm handing over back to you for the future and the speakers. Thank you for coming.
This all right? Thanks, Cyril, and thank you for hosting me and being such a wonderful generous host. And many of you, I haven't spoken to you yet, but the lunch from the Mensa, but not that research. So I'll use this opportunity to introduce myself. My path had changed, and I was working in mining, underground pipe inspection, and then more recently, mainly in livestock. I'm from Australia. Maybe you can see I have an Australian accent. I was born there, but I spent about 14 years in Serbia. My parents are from there, and I was on a farm as a teenager, really trying to escape and not be on the farm anymore. And it's closed full circle, I'm back doing research in ag. So just to introduce a little bit where I am from. So University of Technology Sydney, it's got 45,000 students. And it's a relatively young university in 1988 when it was established. And the employment ranks in things like AI, robotics, forensics, so disciplines that are not traditional disciplines that the university is used to teach, but are more newer. We have 5 locations in Sydney. Our hub is based in the actual centre, Central Station, because it's kind of the largest train station in Sydney. Sydney's got 4 million population. But we also have other facilities that are dedicated to sports, and we have a large industry collaboration centre with defence and space that is based on here in a shuttle in all those hubs. So I've been at university since I graduated. I stayed and worked in the Centre of Autonomous Systems, which was large. At that time, it was larger than in terms of staff and the works, and then I stayed as we have many faculties at ETS, the Faculty of Engineering and IT. The school is Mechanical and Electronic, so that's what their group is as. And then within that school, we actually have 3 research centres that we collaborate closely. One with the Robotics Institute and Mechatronics Robotics, and there's a Centre for Acoustics and Vibration and Advanced Manufacturing. Our institute, so here it seems like institute centres have one professor. We have a number of staff that is in one research. The Robotics Institute, we have 13 senior academics, 4 or 5 professors, 20 early career researchers. We have 50 students, and that's the research income snapshot in 2022 that brought on board. But fundamentally, we do a lot of industry research. So 75% of our income is actually generated from industry projects with large companies or custodians of a problem and our collaborative plans, because our funding is from different. I think we have a visitor, Teresa, who's our chief head of school, and she'll be talking mainly about our general research. It's been in inspecting infrastructure largely, large things that need to be serviced, like the City Harbour Bridge and underground pipes. So we've done quite a lot of that in May. And then the other things that we moved to is timber construction. It's kind of a bit more sustainable, and there's a large push in Australia for it. Surgical plant robotics, space and defence, teams of robots, and on the livestock trade. So why is this focus for Australia in general? So that map is Australia. We're here in Sydney. You can see here this is all green, but this large part is pretty much desert. And well, up here you have a lot of coal being extracted and shipped. So the largest use of coal at the moment is decreasing and going sustainable. But you can see there's an arable land in a large amount of green here that is used for growing crops. Broad acre in here, but a lot of cattle. So that's cattle is for each state, states. So this is both cattle numbers and sheep numbers. And at the moment, Australia is the second largest beef producer in the world. Contributes something like 50% of all sheep meat is actually produced in Australia. World, and 45% of all milk in the world is produced in Australia. So a really large producer of both beef, sheep, and wool. And for scale, there, oh no, but the whole continental Europe can pretty much fit within Australia in terms of size. So if you wonder how that the scale is basically the size. So there's been an increasing push to acquire more individual level planning data, and it's driven by a couple of reasons. First, sustainability, to ensure that a product is sustainably produced. Second, to track any issues. Australia's exporting a lot to China, and if there's any issue, they want trace it back to the individual animal rather than shutting the whole industries, which we've had happen in wine, where we've prohibited any exports, and barley, even exporting in China for an issue that they had. So the other reason is to improve genetics, and improve productivity and reduce waste. So again, underpinning sustainability. With live cattle, at the moment, the things that are measured is fatness, yield muscle score, and frame score, which is size. And in Australia, each industry, so let's say cattle or red meat in general, there's an organisation that collects levies. Anytime there's a transaction that occurs, they collect a certain amount of money. So for every $1, they'll get 0.2 cents. And they put that in and invest into R&D to solve large industry problems, including generating new data. For meat after it's been slaughtered and provide it to consumers, there's a group called Australian Meat Processing Corporation. So again, any transaction there, you collect and invest. And at the moment, we're looking at meat quality and lean meat. So how much fat and how much muscle is on there, and that's driven by us for consumers. When we go to the supermarket, you don't like something with a certain appeal. Therefore, the product should match that and get this back basically up the chain through to the individual farmer. And wool quality at the moment, any presence of contaminants and the folic or the fibre dominant, they impact the value of the wool. So if the wool has a contaminant, you can't really then dye, you can't accept colour, and you won't look uniform, and that goes all the way back to the farm. So this is Australia's wool innovation vehicles for levies, and therefore we invest in some aspects in robotics, but we're looking at animal science. So the three projects I'll kind of pick to show you guys what we've done are with three different stakeholders or custodians of both money, and kind of invest in not just development, but also research, because they acknowledge that you can't just get a product out there and transfer it into this particular industry. So we'll be lucky enough to actually secure funding on all these three. There are funders in grains, horticulture. We are So what is used in training and management of cattle? So if you have a group of cattle, and this is actually from this morning downloaded how much cattle there is. And you go down and check what you have, how many kilos the animal has, and then you check this thing called muscle score, which kind of indicates how much muscle is on the animal, and a fat score, and then is how much money you're spending. So as an individual producer, if you go and collect these values, you can estimate how much your cattle is worth now. You can estimate how much it's worth in sale. You can also estimate how much you generate, and sometimes banks will give you a loan based on future value. But these are very coarse values, and I'll elaborate now. They're called muscle and fat score. But if you're selling something of higher value, so let's say that is a bull, and its value is probably about 20,000 euro, if you want to sell it, then you actually need to get some more finer. So this is P8 fat, rib fat, bone muscle area, intramuscular fat. They're measurements that can't be obtained just by looking at the animal now. There's a way to get those values. And what we want to do is actually not just get these, but these ones. So if you could get these values for your whole herd, you know exactly how much value they are in dollar. Finer in this average. And then how they're also used, well, there are these rough tools that if you know what your animal is currently, so how much it weighs, how much pH, how much bone muscle area, and you know how you're going to feed it, how much grass you have, or how much grain you're going to feed it. You keep the height number, will tell you in 70 days, 50 days, 100 days. So you can predict forward. So if you have a value now, you can predict forward in the future how much value you generate, and you can decide whether you want to feed it for X many days. So this is a coarse way of getting started, and that is a fine way and a much better way in which you can feed into tools and get much better estimates. So the very coarse way of estimating this is by looking at the animal, and there's these scores, and you saw the season average one, and you can see this is like a lightest in terms of muscling, and this is the most muscling that an animal has. This is what's been given to the farmer. This is what they can compare your animal against this, and you can estimate how much to it. And what they're looking at is kind of what's here, the shape, what's up here, how thick it is through here, and how it's standing. So a few things that then you need to match. For fat, it's similar. You have a look, and then you say, okay, how much is in here fat? Is it round? Is it convex? Is it concave? So you could do that if you're an expert. Maybe you get closer and actually have assessors that you can go and bring to the farm, and they'll do it for you, and they'll guarantee you they're close enough to these measurements. But if you want to do it to the high accuracy, then you have to get some ultrasound scanner. So you're going to have to pin down the animal, and put your hand there, and then sometimes remove some of the coat because they can oil to lubricate, like you do with ultrasound. So not only are you holding the animal down and you get stressed, but also it's pretty dangerous. You're putting that here. Imagine if the animal goes up and you lose an arm, and the animal's 600 kilos. So what they're looking in these screens is pretty much this cross section here, and they're trying to measure the area there, which is known as the eye muscle. So it's a very expensive cut. Yesterday, my wife went to a railway supermarket and bought meat, and she didn't notice there was a price, and it was €53 a kilo. It was good. But that's what they're looking at. That's the cut, and they're measuring how much fat is on that area using the others. So this takes 10 to 15 minutes for animals. I like to stop it, so I like to then measure it. These guys that I've done doesn't, they're not really easy to find. I've spoken to Matthew who's here. He goes all over the country pretty much in this truck measuring. So there's a demand for it. But what we understood was the key to this approach was finding key points, finding points from the animal that are consistent. So if you find this point of this animal and this point of this animal, this is the point that guides you in terms of finding information. These cattle are all black, and there's no RGB here that can help you in this. They're Angus, and 48% of all cattle have been straight. and Australia is a large country, so the north of it has a different type of cattle that are not as good quality for eating as the Angus cattle breeds. They're Boston. So most of the value is in this cattle, so we can't avoid that. Also, curvature is important. So everything is related to how the shape is. So whether it's convex or concave, and as humans, we're actually way better at judging whether two shapes are similar in terms of curvature than we are with distances. So I gave two shapes and I said, can you tell me how far, like how long this is? And when you I said, what's more convex or concave? It's much easier. So with distance, we can't really put this neurologically, so we found some papers that support that. But there are issues. So as you can see, the issues are both evident here, as they are somewhat here, being that the position of the leg actually influences how that shape performs. So when it's like this and like that, the volume is similar, but the actual shape of the itself changes. And this animal is just more there, so basically they do that and then pounce. And then when they walk, obviously they form. So you need to deal with being able to find key points and shape, reason about shape, while something is moving, which poses a challenge. We also need to ensure safety for cattle operators, so we can't put cameras out there in the paddock, and we need to operate at line speed. So we usually bring them in, which is an occasion, and weigh them. They go through a weight scale, put them in, weigh them, let them out. And that takes 30 seconds. So we need to undertake all the estimation, everything that we need to do in 30 seconds. Otherwise, it would be impossible. So obviously, there's a data acquisition problem, then there's a key point extraction problem. There's no state completion problem, which we want to avoid it, but there is dealing with deformation. So data acquisition, this one was the. Obviously, we want to get shape good enough to use depth cameras in order to make something that can fit within a standard practice. This is where they rate them. We need to fit it in here. Too close, you can't see enough. Too far, your depth estimate is poor. So we need to do some optimization in terms of finding what suitable camera poses are to deal with different lengths of animal, the weight of look at that. And then once we solve that, then we could acquire the cattle that come through, and the fidelity of the accuracy kind of the curvature is really reasonable for us. And obviously there's noise. There's noise wherever you're perpendicular to a surface. Sorry, we're talking about the surface, right? But thinking within a certain range, the data itself is very reasonable. So I didn't know it was going to be here, but when you click on robotics, because this, which will not surprise you, everything else is animal specific, but obviously, if you're trying to find key points, you want some kind of code network to find the key points themselves. We wanted to deal with calibration noise that could exist because we install it and move it, and install it and remove it. It's not necessarily always the same. It's minor differences. So we've got this network using KP-Con, unlike the Noxkey that's later here. So you guys do. But that let us find key points that we can consistently extract across animals. So that was the first thing we need to find. So these key points might not relate to where you want to measure something, but they're stable and they can be detected whenever the animal moves around. The larger problem was now being able to relate one animal to an animal, or even better, have a canonical model, a model that has annotations on it of areas that are of interest, and be able to use that model and morph it into the animal. So we have a model, we have annotated the areas we're interested in. We'll take that model and now move it to the animal, extract the animal we can't see in the same areas. So we have those sparse key points that we match. Now we have a point cloud, we have a distance on a manifold that we can compute, like a heat current that we can use. And in our bag of tricks, we also have sparse to dense matching, and you can use computer graphics, embedded information, or Jupyter, which are approaches to information. So if you have anchor points, then you can deform between the canonical model, the new viewed animal going over the surface and minimizing the error with respect to surface norms and distance. So obviously we couldn't test this on animals because we're not going to pose there for us and move. So instead, there's our house. It's a data set that has, I think, about 100 or something humans, and they have put stickers on them so that they can locate the same points. You can download the data set, and then you can morph from one person to the next person in many different poses. So we evaluated how well this approach has been developed. We tried to use some including functional maps, which wouldn't really be symmetric in some cases. But we proved that we could do better than functional maps, and that this was a very neat way to do annotation. So once you do annotation transfer, you go from this to a person, then you can separate out all the parts of this thing. So if you look at the animal, things that only in some parts have them. If you encoded the whole thing as one signature, there's too much dimensionality, we don't have as many samples. So we needed a really compact signature that just has the area we're interested in, and then we can get one units and so so this is on the animal. You get the key points. We have this point cloud, there's a mesh underneath, there's some optimization, it's perfectly top of it, it's correct with the area. So once we have this, we have consistently the same areas, then we can do the standard learning of, supervised learning of traits versus some feature, like curvature or any other. We then roll this out. This is actually at so we have a good engineer that was looking. That's our partner from industry partner from the EU itself. So maybe I'm not sure whether you saw that working, but so when they put the animal in, currently it's green because there's no animal in there. When we detect animal, we go orange, and then we're examining as it moves where the shot with the feet close enough together. We fire it red, and then now it's moving green. So the estimate is within a few seconds. And that's kind of what I was talking about, the key points and the information. And we estimate some of the traits with supervised learning, so the P8 and key points. He's going to feed it to the next thing, which is the sorry. Because of what he wants to pass forward. But once it goes through here, it goes into the scale. They get the weight, get the RFID, because that's the only thing that's consistent, so they can track the weight, and then it gets fed into that engine that I was showing at the very beginning of my slides, where you give it the current weight, the current pH, and you predict forward in 70 days how much trade it is. So we integrated that from end to end. So how good is this at the moment? So for the meat science experts, ask where's and RMCs and value. This is estimated in pH. This is the estimate from us versus the observed. Acknowledging it's noisy, but we're dealing with things that both move, you don't know quite certain, and secondly, it's one measurement that someone has with pH in one point of the animal, and we're trying to infer from the whole shape is technological. That's kind of going patterns to pH. This is hip height, that's obviously much easier. And then this final one is called the hot carcass weight, and it's the weight of the animal once it's been slaughtered and value got itself, not the live weight. So we're trying to infer all that. There's slightly different numbers of cattle we know because we've only had 30 animals that we've been taken immediately, as in these guys will measure random times during their growth. And since then, we've got another 400s. So to get pushed through. So that's live animal. Now, what happens after slaughter and analysis consumers? Unique. So the value of meat is based on grade. It's based on how much protein or how much red meat's on it versus how much fat's on it. And this is from the US. This is how they grade their meat. So you can see this is like the optimum grade. That's a grade 5. It's too much fat. That doesn't have enough fat. And basically this dictates your price. So if you're P8 and your biomass area you measure on the live animal, and you translate the carcass. Therefore, you know even before slaughter to work, this is added to our slaughterhouse. Didn't quite understand the process, but it's really complex. So in Australia, there's about 30 or something slaughterhouses, and they don't sell just the animal, take the whole thing. They actually sell each individual piece. And kind of like pumping dumpling, once you cut this up, you can't put it back together. You can't go, hey, can you give me more of those? No, it's done. So you have to decide where you're going to sell it immediately after they come in. And therefore, you need some estimates of its value, and then large machine learning models that they can say, okay, today's prices, we're going to send all tons, big tons to Thailand. We're going to send all this, and they just go to all these different places. But then you need to have an indication of this product value. So the two values that you kind of need at minimum is, again, the amount of fat and the amount of muscle, which is based on the amount of that surface area plus the size of the animal. So if you're no surprise, we then also took our livestock scanner into an abattoir and just set it up slightly differently. So it rotates around, scans, and the same thing, shape, deformation, limitations, and we can estimate roughly how much muscles in there. But fat proved to be a much difficult challenge because it's just, shape, and it's much harder when carcass it's not suspended and you can't see the muscles very well. So literature suggests that you can measure fat or body mass index using near infrared or short wave infrared. And so we were keen to see whether that's possible, and given that we can reconstruct the carcass very well, and we can deal with cameras, calibration, we know where one camera is to another. We have another white source camera and a line scan camera that can do many spectral things. So we thought, great, we'll do that, but then we have to take a step back and go, how can we get ground truth? If we estimated how much fat is at each individual point here, how do we train this model? And it became much harder than it's a whole carcass to develop this, because you can't, if you scan this and then we take it down, it's going to perform. And it's going to perform a lot. And even add a bit of information. So if you want to put it through a CT machine and measure how much fat it is and then relate it back, that's so much harder. So instead, we said, okay, let's take a step back and do something that doesn't perform as much between CT scanning and scanning. So this is just the same setup with our hyperspectral camera, light source, and our 3D sensor there. That's the L515, the real sensor that existed. We scan this. This hyperspectral camera is a line scanning camera. It's $80, so we get one of those scans. The whole image was a salary of 3 postdocs on my center directs. You have to do this, so I just use this for line scan. Anyway, so we can scan them as they come through, and then we can put them on a tray, take them to next door, which they have a CT machine, scan them through, and actually get CT scans that tell us how much muscle and fat is actually there. But the challenge was actually quite large and work of one PhD. So I have a PhD student who's solely working on solving this. There's actually a few things happening here. So you have a light source. You need a light source, ideally one you can control, because this hyperspectral camera actually separates lights into about 200 or something bins, and it does it with a series of mirrors. So you get 250 of natural light. So you need to inject a whole heap of light into it. So you need a powerful light source. But that light source is separated from the camera. We don't know its properties. It bounces onto the surface. So this is the light source. This is the hyperspectral camera. This is the RGB camera. This is the information between it. But that light goes onto the meat. When it's on the meat, some bounces just from the surface. Some penetrates the surface and goes in through the fat cells and radiates back. And that's the one that we want, because that would be related to how much fat there is. And then when it goes into the muscle kind of like fiber. So the one for light goes in and it's trapped. And it goes out, so it doesn't bounce. And because we have a piece like that, we either have fat, muscle on the surface, and then underneath fat is muscle. So if we can just capture that light, it bounces it because it's trapped inside the fat cells and bounces back rather than spectral component and growth. And obviously the curse of the dimensionality of the hyperspectral camera is now 200 something there. So we went on it in 3 steps. First, we modeled the light source. If you model the light source, then you know how much light gets to the surface, right? And you know, you can use a calibration board and some kind of material that's burning the target. And you just through finite measurements, you can then feed it into a GP, knowing that it's a nice tropical asymmetric light, and we can get then a really nice representation of it, including itself, obviously within the field, ends up being instead of very low, or we can model it, and therefore now we can put it in anything underneath it, or any orientation, and you know exactly how much light reaches the surface. But we don't know how much light then goes inside it, and how much light returns back. And thankfully, we had a postdoc from Carnegie Mellon who was with us for 1 year, and she was in forensics. And there's a way that we can actually measure that. If you know the radius comes to the surface, and you know the surface normals, you can fit through an optimization, and that breaks the light into 3 components: specs, specular coefficient, shading, and the resistance. That's what we need. Okay, so we needed both a 3D construction and we needed a light source modeling, and then through optimization, knowing the surface orientation and where the camera is, we can break the material. So once we did that, then we can through now this estimate of weapons. We have many things, but we can feed it through any style, either deep learning framework or just NLP. And this is base cut. And this is the error that we have in estimating the fat. So these here are the fat depth, and we can see if we use this network or the other one, the errors are much lower than if you start at a linear regression or simple NLP, which was great, because then we could go and actually estimate fat, and we can tell you exactly how much fat depth is across this carcass. So for each point along it, not just one point, but for each pixel, we can tell you how much fat is in it. So that was good. That was great. But we put it on down in close full circle. We can go down and actually included it on our nice rig. But the key was to exploit 3D shape and exploit the fact that we can model the light source, and then move any other surface kind of properties and just concentrate on light source interacting inside the facts. So slightly changing tack, and this is the third body of work that aligns with the research direction of the Australian Wool Institute. As I said, it's 45% of all the wool in Australia is produced. So, yeah, all wool in the world is actually produced in Australia. It's a large driver of our economy. A very manual process. Agriculture in general, still not many, but wool processing especially. Given that Australia produces so much wool, it actually drives the effort of automation. And in the 90s, they tried to do an automated shearing robot and sunk many millions of dollars into that. The technology was then very immature. So they wanted to revisit some level of automation, but they insisted that we don't look at shearing. It's a hard problem. And shearing is the removing of the wool, and it's a very hard process, very manual. Lifespan of someone who does this, workspan is very about 10 years. After that, you hold in the animals, let's say foot, and then using other four-wheel limbs to actually control something that weighs 40, 50 kilos, and you flip it around and remove it. They're really good. And in Australia, we have in spring we have a show, and they come and actually show how fast there's competition, how good you are to get ranked. There's world champions and Guinness record. But after that's removed, the wool is usually removed. They do it so well, it's in one piece. And they throw it out on what is known as a skirting table, and then have to inspect and remove contaminants. If contaminants are in there, once they get sold, they'll be in there and you get reduced premium. And obviously, once they reach the buyer, if the buyer gets something that's contaminated, it's even worse. The contaminants are varied, and this is a shearing shed. So you can see here there's, I think, 6 shearers. This is a new one, and then there's 1 or 2 people that go between to get this, and they roll it out, and they have to inspect it within 1 minute. The whole fleece, and so obviously they're cutting horns, or just doing it for the sake, but they're actually not removing contaminants. And then there's a process where they have to look at this and determine how much micron value it is based on how they feel, which tells you how much value it is, and then they put it in bale. So the shearing sheds are made, and it's very hard to attract people. In the pandemic, it was really hard. We couldn't get any models in Australia, but even now, we're always competing with New Zealand and getting starts. And it's not something you can learn easy. So the backpack comes, we get pick fruit, but to shear a sheep is completely important. So Australian Wool Institute said, okay, don't look at shearing, but look at the handling part, which is detecting and removing contaminants, classing, and then pressing and sealing the label. So we ran a project across 2.5 years to look at various steps along this problem space. I'll just show one. I'll show you detecting and removing contaminants. And this pricing one, just for time. So this is how they staggered our development. So this is what I'm going to show in a little more detail. And then the other part, fiber, mean fiber perimeter, that's so detecting contaminants, the difficulty here is there's no other system that's trained that can detect contaminants. So we're developing something that's first. You can't push this through a airport scan or something like that. So the Australian Wool Institute said, look, we have people that are really good at this, and they'll take their time, and you'll be able to collect data as they're removing it. And basically, as they're removing it, so this is them showing how to scale it. This is a manual.
In this section, you will see a demonstration of overscooting. That will be in part green for instance.
That's what they're doing.
Overscooting.
So the guy goes, scripts through, rolls it over, picks some stuff on the bottom, and then that's done. So we're all like, I don't know how you can identify where the contaminant is there. And this is just an image of before. So this is before, and this is after the skirt. And visually, they look almost the same. So there are areas on the fleece that actually do match. So if you gave it to some kind of, not deep learning, because we don't have ground truth, we're training deep learning network specific for wool, but you go to any features there, like caves, SIF, risk, or something like that, they can pick some features. Some very limited, right? So we can't record as they're doing it because they're pulling with one hand and pressing down to secure. So it's really hard to record data as they're doing it to inform you where to remove. But as we figured out, the key again is going as fast against doing as much as you can with additional feature extractor, including some network to learn spatial representations, and then we leverage again deformation and model for the livestock into this problem. So we instrumented or we collect a lot of wool where we actually put markers. We can find correspondences, and therefore we can train something like the MLP that we give these fast correspondences and orientation to others, and then find the match. And so we go fast, to dense, and then propagate everything through as far as we can up to the skirting line. So this is kind of the sparse correspondence before we feed it through a network, and then all in blue is all the ones that are matched once we feed it through an MMP. So if we can find where the wool was before, where the wool was after, we detect the part that's removed from the original image, we use that one to train a network to detect that in effectively. So we've done that, and in the meantime, we've also thought, okay, this problem seems to be persistent, where whenever we pull wool, it deforms a lot. Is there some way that you can model this using some engines that exist for physics for information? We found neatly that okay. Yeah. So these are physics-based. Oh, sorry, I'm not sure. Yeah, here we go. So these are physics-based engines that model deformation. So if you have material, if you can estimate material properties, yeah, so practical material. So if you can, obviously this is computer graphics. So here they basically have everything observable, and they're simulating tearing where basically they've artificially created this piece of red. But in that, they have to create the voids there, right? So the challenge going from computer graphics to robotics has always been you don't perceive all the properties. You have to invert it, and secondly, your sensor is not going to really be able to see through the red to the other side, right? So you can't just plug in something like this straight into a robotics problem. And what we realized is there's a few things you need to know. You need to know where you're applying force. So we know that. So this is like separating fingers down. We know where you're applying force. You also can estimate the fiber orientations and directions. So if we look from the top and from the bottom, you can see where the fibers are oriented. Okay. We also know how tall the fleece is. So we have pretty much a lot of it in 3D, including fiber orientations. So if we can do that, now the missing parameters that we need are the youngest module, elasticity, and everything else. But if you took one fleece, because remember fleece is really big and it's all along the edge, you could learn the parameters from the first pull, and then you could apply and know what's going to happen to us. So that's what we've done. So we take one piece, wool, we can try and learn the parameters of elasticity, and then we can just apply them and know even before we pull where the line of separation is. And that's important because if you want to orient the skirting line and remove this, you need to know how to do that. So this was submitted to us. We didn't actually get it. So maybe I'm sure that's and yeah, so the other thing is building a system that can do this. We went through a few iterations. Normal skirting tables are like this with rollers. The wool, if the wool falls in between the roller, it's gone. So instead, these style of conveyors, some kind of drop downs. We did manage to train a network that can do, predicting where it might move, using that data we got. And we did demo actually, and then we're quite happy. The schedule was there to look. And the only thing that was missing, I think, in one of the corners, he lifted it up and underneath was another piece we obviously can see. So we now have the cameras on both sides. And this is the first attempt that we had at removing things. So we didn't want to use one of those pools, and we tried to use this belt one. Actually works okay. You have to hold the fleece down. That's a thing with rollers, and then from pulls at an angle that we improvingly tune, and also goes backward and forward, removing large pieces, and goes to a suction system, and yeah. So that's, I think, all. This is a snapshot of my team for the last few years. The resume is over here. A few engineers have already gone to industry, very happy to keep people that are good, PhD students, and we have a large amount of people that have helped from New South Wales DPI, which is their livestock experts. So I think that's all I have.